Hi, I'm Meraj from the Ohio State University. Today I'll be presenting our work data tweening, which is an incremental way of visualizing structured data transformations. This is a joint work with my advisor Arnab Nandi and Larry Shu and Joe Hellerstein from Berkeley. Tweening, a contraction of the phrase in betweening, is taken from the animation world. It is defined as interpolating frames to smooth transition between two distant states or keyframes. In this figure, showing a kangaroo jump, with the first keyframe showing it at rest and the second showing it mid-air, tweening would be generation of these intermediate red frames to show a smooth transition between these two states. We define data tweening as interpolating between consecutive result sets in a query session. We do this by breaking down a transformation into basic structural transforms while highlighting the parts of the table undergoing these transforms. For instance, consider this data transformation corresponding to a change in where clause which includes deletion and insertion of a few rows. Tweening for this transformation would be generating immediate result sets to show these changes. So deleting these rows and then inserting these rows. So why do we need data tweening? With advancement in database technology and new client devices, the way we interact with data has changed dramatically. We are no longer confined to a question answering paradigm of interaction where a user would key in a query and wait for the result to show up. We can now directly manipulate data table, issuing new queries with continuous user interactions. Data analysis tasks in this world are now often interactive query sessions where the result of each query in the session helps the user frame the next query. Often in these sessions, between two result set changes, small changes might often go unnoticed and they could be critical. Also, if there are drastic changes in the results, it could be disorienting for the users. Moreover, on the modern interfaces, instantaneous and helpful feedback is kind of a hard requirement. A discrete transition between results caused by query changes from continuous user actions would break the illusion of direct manipulation. We address these problems with the following contribution in our current work. The concept of tweening itself. We define a visual grammar of basic structural transforms and visual cues to represent these tweening sequences, and we provide a framework to generate these tweening sequences for a subset of SQL. What makes tweening challenging? We are talking about animating data transformations. Animations have proven to unexpectedly complicate things in certain use cases, so we must make sure that doesn't happen here. Also, currently there is no standardized way of expressing tabular transformations, and we have to make sure tweening doesn't affect the query execution time by a great margin, which might hamper the user interactivity. We use a two-space model for describing tweening. The standard space is the standard visualization space in which the traditional query interfaces operate. Issuing a new query QNew would change the result set instantaneously. The tweening space breaks down this transition into intermediate steps. The tweening space is characterized by visual cues such as gaps and color highlights, and we use a nested relational model to represent the intermediate states. This is because the nested relational model provides a more intuitive hierarchical representation for aggregation compared to the relational model. We formalized a visual grammar to encode transitions between distinct result sets. The grammar is a set of micro-operations. The micro-operations could be one of the following types: transforms, which represent basic structural and data transforms, so like inserting a table row or column or deleting it, and visual cues, which draw a user's attention to parts of the table undergoing these transforms. Each micro-operation in a tweening sequence has an index parameter specifying which parts of the intermediate result set it would be acting on. Any change in result set can be visualized as an ordered sequence of these micro-operations from the grammar. For instance, an insert micro-operation on this table at row 2 with that particular data would change the result set to this new result set. Similarly, a visual cue for highlighting a table part would change the result set as follows. There's a complete list of these micro-operations in the paper, and the grammar is complete in the sense it can encode every transition between any two SQL result sets in the entire space of SQL. Now that we have defined a formal way to encode tweening sequences, we can look at tweening framework, which automatically generates tweening sequence for a given pair of consecutive queries and their corresponding result sets. We could do this in two ways: result-based tweening, which would just compare the two result sets and not take into account the query changes, and query-based tweening, which would take into account both the query changes and the result sets. The most basic way of doing result-based tweening would be considering the result sets as grids and diffing the two grids to come up with an incremental row and or column edits with visual cues. Alternatively, we can consider result sets as ordered trees and use minimum tree edit distance algorithms to find cell level edit sequences. This is useful in cases like cross tabulation, where transposing of cells cannot be represented by naive grid diffing. So what do we mean by naive grid diffing? For instance, if we consider the new result set R new, which is a result of transformation from the original result set R old, we can just take a diff of these two tables to see the column C needs to be deleted, and there's insertion of a new column D, and finally we have a new row in the old result set, giving us the final result set R new. Now, result-based tweening has certain limitations. There is no representative tweening for aggregation or pivot. Aggregation transformations with result-based tweening would have no way of showing aggregation from constituent tuples. We define also result-based tweening generally has a high visual cost. This is especially true for tree-based tree diff approach. We define visual cost as the number of contiguous table blocks undergoing changes between two consecutive micro operations. Tree diff approach works on cell level, which causes a high number of edits between each frame. Also, there could be a few ambiguities between in the transformation using result-based tweening. For instance, it is hard to determine what was the change in the query for a result-based tweening. So for example, for this particular transformation, the result-based tweening would be showing deletion of these two rows. Now, this deletion could be because of a new where clause condition, Surrey not equal to London, or it could be because of a new where clause on the last name not equal to Smith. So to deal with this, we came up with query-based tweening, which essentially uses a rule base with template tweening sequences. Changes in query defines the sequence of micro operation in the tweening sequence. So going back to our original transformation, with if the new where clause was on last name not equal to Smith, we could define the new tweening sequence as this. And instead, if the where clause was on city, we could define the tweening sequence as this. And we could essentially distinguish between these two sequences, which was not possible with result-based tweening. When one or both queries are aggregation queries, just the corresponding result sets might not be enough to show aggregation from constituent tuples. So in this case, we issue a new query different from the actual query issued by the user and perform the aggregation on the client. So for example, if the original query was a select query with this particular where clause, and the new query issued was an aggregation query but with no where clause, we would issue a select query with no where clause, so that we could essentially show aggregation for the Q new query from this Q issue query, which wouldn't have been possible if we used the result from the Q old query. We inserted certain optimizations in our tweening sequences, one of them being reflow optimization. So reflow is the UI process of calculating the new positions of UI elements on the screen with each transformation. Now we want to minimize the points of changes between each transformation. So to do that, before each data transformation, between each data transforming micro operation in the tweening sequence, we perform an ordering of rows and check which of the ordering would result in minimum visual cost between consecutive operations. And we use only single column orderings to determine a minimum cost order. And this is because if we considered orderings on multiple columns, it would result, it would just blow up the computation. So for example, in this transformation, if you see the first half of the screen, the transformation has 3 points of changes in this table. But if we inserted an order operation on the year column, we could reduce the points of changes to 1. So how do we study if tweening is an effective visualization method? We came up with these 3 hypotheses. Tweening does not negatively affect users' understanding of transformation, which was one of our primary stated goals. We also need to see if tweening helps understand and retain changes during transformations for users. And finally, we want tweening to enable users to help understand and learn complex transformations. So for testing the first hypothesis, we conducted an online survey on Amazon Mechanical Turk, and we randomly assigned 50 Turkers for each of these tasks, for these 5 tasks. Each of these tasks were basic changes in the SQL query or basic relational algebra operation like selection or projection. And the users were shown a tween transformation for these corresponding changes, and we asked the users to identify what the changes in the query were or what was the corresponding relational algebra operation. And as you can see, most of the users could easily identify these transformations, and they also said they found it helpful. To understand if tweening helps understand and retain changes during transformations, we conducted a between group study on Mechanical Turk with 50 users per group per task. So the 2 groups were a tween group, which was shown a tween version of a certain transformation, and then the non-tween group, which was shown the same transformation but without tweening. To each of these groups, we asked questions about changes in the transformation, and we assigned them a score, which was basically the difference between the actual value and the user response. And then we compared the score distribution between these 2 groups with a Mann-Whitney U-test. So for the basic transformations, we used changes in select clause, where clause, and group by clause as 3 tasks. And for a different use case, we defined a chain of transformations which had a change in select clause followed by a change in where clause followed by a change in group by clause, and the users were asked to track changes throughout this transformation. And you can see the group difference is statistically significant for a significance level of 0.05 for all these tasks between the tween and non-tween groups. Now to finally, for testing our final hypothesis that tweening helps understand and learn complex transformations, we first identified pivot as a complex transformation from a user survey with about 200 users. And then we conducted an in-person user study where we asked 20 users to rate our pivot transformation tweening on 2 scales, understandability and clarity. So understandability here means if the tweening transformation helped the user understand how pivot transformation works. And the clarity attribute means if the tweening transformation, it was easy for users to follow changes in that sequence. Both these attributes were scored between 0 to 10. So this is the clarity chart. On the x-axis, you have the 20 users. On the y-axis, you have the rating from 0 to 10. You can see most of the users rated the tweening sequences for clarity more than 8, with the mean being 8.25. And on this understandability chart, you can see most of the users rated the tweening sequence again more than 8, with the mean being 8.5. Finally, we studied the tweening framework's efficiency from the performance standpoint. That is, introducing tweening in a query session does not hamper the interactivity. So to do that, we set up a web app running SQL.js in Google Chrome on an Ubuntu PC. And we tested 2 different workloads. First was an OLAP session generated using kubeload on the IPUMS database. We extracted a 2,000 tuple sample from the 1980 US census. And for the second workload, we took query sessions generated from user studies in the distributed and interactive cube exploration paper from ICD 2014. So for the IPUMS dataset, the total execution time, that is the execution time for the entire query session, you can see that the without tweening execution time compared to the with tweening execution time on the chart on left, where the execution time is given in milliseconds, and the difference in the two is not too high. The average query execution time, which is average execution time per query, it's hardly 5 milliseconds for without tweening query times at 64 milliseconds. And for the data center workload, the changes are even smaller, and you can hardly see any difference for the average query execution time, almost just 1 millisecond without tweening and with tweening. So we can conclude that tweening makes data transforms more informative. They do not negatively affect users' understanding. On the basis of our user studies and on the basis of our performance experiment, we can conclude it does not add significant overhead to execution. And also from our surveys, we could conclude that users prefer tweening or the incremental visualization. For future work, one obvious direction is tweening for large result sets. The current work only covers result sets which can be fit on a user screen. So one way of doing this would be creating template tweening sequences over representative samples, or alternatives, or we could use alternatives to text table visualization such as table lens. Another thing would be creating query specification interfaces with tweening enabled, and then we could see if tweening actually helps user in the data analysis tasks and make them better at it. Thank you.